Welcome to this class. Today we are continuing the chapter Force and Motion of the subject Science and Technology of class 10, and this chapter is taken in unit number 7. In previous class we discussed about the gravitation, gravity and other terms also like acceleration due to gravity, gravitational constant, etc. etc. Now this is fifth part. Out of 6 part, we have divided this force and motion into 6 part. Out of 6 part, this is second last part, I mean to say fifth part. In this part, we are going to focus on capital G, small g, difference between capital G and small g, gravitational constant and acceleration constant, differences. And then we'll talk about the differences between mass and weight. First, what is mass and what is weight, and then we'll go through different differences between mass and weight. And at last, I'll tell you about the free fall also and the numerical problem related to free fall. Okay, let's start. We have to differentiate capital G and small g with many points. So, at first, I want to recall their definition, gravitational constant and acceleration due to gravity, and then differences. Look at this. What is gravitational constant? What I told you, if we have 1 kilogram mass, another 1 kilogram mass, then we can say that we have 2 unit masses. And if they are placed at the distance of 1 meter, we can say that 2 unit masses are taken in 1 unit distance. The distance between them is 1 unit. Now, the gravitational force which involves between them is called gravitational constant. So, we can define this way: the force of attraction between 2 unit masses separated by a unit distance is called gravitational constant. It is denoted by the symbol capital G. Be clear about this. Not F, capital G. Gravitation is denoted by F because it is force, and gravity is denoted by F, capital F. It is also a force, but gravitational constant is denoted by capital G. We have to be clear about this first. Now next, acceleration due to gravity. What is it? This is just the acceleration, but due to gravity force. Acceleration developed on a freely falling body due to the gravity of the earth is called acceleration due to gravity, and it is symbolized by small g. Now looking at this symbol, you have to be clear. Capital G, gravitational constant, small g, acceleration due to gravity. Okay. Now we are going to differentiate capital G and small g with different differences. Look at this. Capital G, what is it? It is gravitational constant. And small g, what is it? This is the symbol of what? Acceleration due to gravity. Now second difference, we can say that capital G, we can define them and definition can be expressed as second difference. Gravitational force between 2 unit masses separated by a unit distance is called capital G. But the acceleration developed on a freely falling body due to the gravity of the earth is called acceleration due to gravity. Now third, we can differentiate them with their value. Its value is 6.67 into 10 to the power minus 11 Newton meter square by kg square. Value with units. Capital G, this is a constant and its value is this. But small g, its standard value is 9.8 meter per second square. This is one difference between capital G and small g. Now another, this is a scalar quantity and this is vector quantity. If you remember, what is vector, what is a scalar? A physical quantity expressed only in terms of magnitude is called scalar quantity, but a physical quantity which is expressed in terms of magnitude and direction both is called vector quantity. Now small g is vector quantity because if you remember the value of g, I told you 9.8 meter per second square. Here, this number and this unit, both of them represents magnitude of acceleration due to gravity. But what about direction? Direction of acceleration due to gravity is towards the center of the earth. If a body is dropped from certain height, it tends to go towards the center of the earth. Its direction is fixed. That's why this acceleration due to gravity is expressed in terms of magnitude as well as direction. That's why this is a vector quantity. But the gravitational constant has only the magnitude. Here we have numbers and unit, which is actually magnitude of capital Z, but this is not unidirectional force. That's why this is scalar quantity. Okay, let's go to another point. Its value remains constant throughout the universe. Wherever we go, the force of attraction between two 1 kg masses, if they are at the distance of 1 meter, is 6.67 into 10 power minus 11 Newton. It never changes. That's why the value remains constant throughout the universe. But the value varies from place to place of the earth. Small z, its value is different in different parts of the earth. A little variation occurs in each and every part of the earth. At the pole, it is 9.83. At equator, it is 9.78. And in other places, its value lies in between these two. It varies from place to place of the earth. These are the basic differences between capital Z and small z. Okay, now I want to go through mass and weight. We are going to differentiate mass and weight with different points. Actually, whenever you go to buy something in grocery, then we used to say that give me the weight 1 kilogram of something, and we think that this is the weight of that substance. But actually, in daily life, we are saying weight, but this is exactly the mass. And this is the difference between mass and weight. Actually, weight is the force of attraction of the earth acting on the body, but mass is quantity of matter contained in the body. So there is a big difference between mass and weight in the study of science, but in daily life, these two are mixed up with each other. That's why I want to start with mass. How can we define mass? It was defined in lower classes also. The quantity of matter contained in a body is the mass of the body. Look at this piece of paper. This is a small piece of paper. This is bigger than the first. The quantity of matter contained in this small piece of paper is less. If we talk about the molecule, maybe just say 1 crore molecule is present in this. But the quantity of matter contained in this big piece of paper, bigger than this one, big piece of paper is not 1 crore molecule only. Quantity of matter is more. That's why quantity of matter contained in this big piece of paper, that is the mass of this big piece of paper, is greater than quantity of matter contained in this small piece of paper. It is less, it is more. But we cannot compare different substances with each other. Just for example, this much big piece of wood may contain less amount of mass, but this small piece of iron may contain more amount of mass. Quantity of matter contained in a small piece of iron will be more, maybe more than this much big piece of wood, because the matter is compact in the iron. I mean to say, quantity of matter is compact in the piece of iron, but it is less in a little big piece of wood. That's why quantity of matter contained in a body is mass. And symbol used to denote mass in the numerical problem is small m. We denote mass by small m in different equations. Next is SI unit is kilogram. but its CGS unit is gram, its FPS unit is pound, but SI unit is kilogram. We are using SI unit in the numerical problem. That's why I am highlighting this kilogram. Next, it is measured by using beam balance. Now we can say it like this. Let's say this is a beam and this is the central part of the beam, and if we have pan at this place and at another end this, and this is very simple representation of beam balance. This is the beam and we have two pan. Wherever we have to measure the mass of a body, then we'll take a standard mass at this place this way, and we'll compare the standard mass with unknown mass, whatever we have to measure. I mean to say, if we have to measure the mass of sugar or potato, whatever we have, that should be taken in another pan, and standard mass should be taken in one pan. And actually, the force of attraction of the earth acting on this standard mass is compared with the force of attraction of the earth acting on this unknown mass. When these two, I mean to say the gravitational force of attraction of earth on this mass is equal to gravitational force of the earth acting on this second mass, then the beam becomes balanced. Beam comes in equilibrium, and we can say that this unknown mass is equivalent with 1 kilogram. I mean to say this is 1 kilogram mass. If it is potato, we measured 1 kilogram potato. This way, beam balance is used to measure the unknown mass. But in the measurement, what is used? Gravity of the earth or gravitational force of the earth acting on the standard mass is compared with gravitational force of the earth acting on the unknown mass. This way, for the measurement of mass, we need gravity of the earth. Okay, next point, what can I say? It is a scalar quantity. If we measure 1 kilogram of sugar, then someone can ask that what is the amount of sugar? Then we can say 1 kilogram. And if someone think about its direction, what is the direction of 1 kilogram sugar? Then question seems to be so funny, isn't it? How can we talk about the direction of mass? How can we talk about the quantity of matter has direction? We cannot talk like this. I mean to say, mass is a scalar quantity. It has only magnitude. It has no any direction. 1 kilogram sugar doesn't have any direction at all. That's why we have to remember this matter. First, definition of mass and what is the symbol used to denote this mass and its unit, and how to measure the mass by using beam balance, and this is a scalar quantity. We have to remember all this. Now I want to tell you one interesting matter related to mass. If you want to measure mass in space, then you cannot measure mass of the body in the space. Mass of the body cannot be measured in the space. This is an interesting matter, that's why I am presenting this matter to you. Look at this is beam balance. If you want to measure mass of certain substance, certain material in the universe, then you can take standard mass in one of the pan like this. When standard mass is taken in one of the pan, then this pan goes down like this. And if you take the material which you want to measure in another pan, then what happens? This pan goes down again. Now, it happens many times. If you try to measure, then when you touch this standard mass, this side of the beam goes down. When you touch this material, then this pan will go down. This way, mass cannot be measured. If you try with the standard mass, let's say 1 kilogram mass is taken in one of the pan, and if you hold this beam and for a few seconds, 1 or 2 seconds, and if you release hand, then what can you see? The beam is balanced without the material. 1 kilogram mass is taken in one of the pan, but beam is balanced. Once if you hold this beam for 1 or 2 seconds and release your hand, then beam is found to be balanced without the material. Very interesting. And if you take this material in one of the pan and the standard mass is removed, and if you hold the beam for a few seconds and if you release the hand, then what is seen? Again the beam is balanced. Nothing is measured. Actually, just taking the material also, the beam is found to be balanced. Just only standard mass is taken, beam is found to be balanced. What is the reason behind all this? Because we cannot measure mass in the universe. There is nothing, no any gravity force, no any gravitational force. Mass is measured by comparing gravitational force of the earth acting on a standard mass with the gravitational force of the earth acting on the unknown mass. If gravitational force of earth is absent, or if we do the same in moon, we can measure the mass because we are using gravitational force of the moon. But in the space, there is nothing. No any heavenly body attracts the standard mass and the material. That's why measurement of mass in the space is not possible. Okay, if the same is question for you, you can say like this: mass of a body is measured by using beam balance, and it is measured by comparing gravitational force acting on an unknown mass with the gravitational force acting on a standard mass. In the space, there is no gravitational force at all. So, mass of the body cannot be measured in the space. We can answer like this. We can argue like this. Now, let's talk about the weight. What is weight? Now, weight can be defined like this: the force with which the earth attracts a body towards its center is called the weight of that body. Just for example, this paper is attracted by the earth. What amount of force is acting on this paper? With what amount of force earth attracts it towards its center, that is the weight of this piece of paper. Now, weight of this marker pen, the force of attraction of earth acting on this marker pen is weight of this marker pen. In the same way, weight of my body means the force of attraction of the earth acting on my body towards its center is the weight of my body. Certainly, weight of this paper is less, but weight of this marker pen is a little more, and weight of my body is more than this too. What is the reason? Reason is very simple. Weight of the body depends upon its mass. We have to remember this also. That's why in terms of measurement, we can define weight this way also. Weight of a body is the product of its mass and acceleration due to gravity. And the formula is W equal to mg. M represents mass, W is weight, g is acceleration due to gravity. If we know the mass of a body, then its weight can be calculated by using the same equation. If we have given 5 kilogram mass and we have to calculate its weight, then using this formula W equal to mg, we can take 5 kg in place of m, and in place of g we can take 9.8 meter per second square, because this is the standard value of small g. Using this value, look at this, 5 into 9.8 gives 4.9, and kg meter per second square is Newton. Thus, we can calculate weight of the body. If mass is known, then its weight can be calculated easily by using this equation. Okay. Now let's go to some detail about the weight, how it depends upon mass and acceleration due to gravity. This is, let's say, a small piece of iron. This is another bigger piece of iron in comparison with the first. The second one is bigger than the first. It means mass of first is less. Mass of second piece of iron is more. And both of them are attracted by the earth. With what amount of force the earth attracts these masses, that is the weight of these masses. That can be calculated by using this equation W equal to mg. Since the mass of first is less and second is more. That's why product of mass and acceleration due to gravity will be more in this second case. G remains same in both the cases, but if mass of second is greater than first, then certainly weight of second body is greater than first body. But in this case, mass is less. That's why weight of this less mass is also less. This way we can relate weight with mass and acceleration due to gravity. Acceleration due to gravity of a certain place remains same. Just for example, in this place, acceleration due to gravity acting on this body and this one or on my body is same. But if I go to some other place, other city, other country, then probably a little variation occurs. But at the same place, G remains same and weight depends upon only mass. Okay, we can describe like this: weight of a body is the product of its mass and acceleration due to gravity. Then symbiotically W equal to mg. G remains same at a place, but mass of a big stone is greater than a small stone, so the product of mass and G, that is weight of big stone, will be more than the small stone. Someone can ask you that why a big stone has greater weight than small stone. That can be answered like this. This is the reason. Okay. After all this, I want to differentiate mass and weight with different points. How many points we can say? Let's say mass and weight is differentiated with many points. We can say thus the definition first. Quantity of matter contained in a body is the mass of that body. But weight, the force with which earth attracts a body towards its center, is the weight of that body. This is one difference between mass and weight. If you are just told to differentiate mass and weight, then you can say just the definition. But if you are told to say different differences between mass and weight, then you can say more than one point. Second point can be, it is measured by using physical balance, which is also called beam balance, which just before this one simple representation of beam balance or physical balance was shown. You have seen that. It is measured by using what? Physical balance. But the weight is measured by using what? Spring balance. Now third difference may be, it is a scalar quantity. It is described just before this slide. I described this. It is a scalar quantity. Which one? Mass. But weight is a vector quantity. How? It has both the magnitude and direction. Just for example, if my body weight is, let's say, 600 Newton, what it mean? 600 Newton is the magnitude of weight, and it has direction also. Weight is the force with which the body is attracted towards the center of the earth. That's why the direction of this weight, 600 Newton weight, is towards the center of the earth. That's why this is vector quantity. Weight is vector quantity, but mass is scalar quantity. Now next, its value remains same at any place of the earth. If this piece of paper is taken to North Pole, then its mass remains same. If it has 1 crore molecule, then at North Pole also, or at South Pole also, or at equator also, the quantity of matter remains same. Number of molecule remains same. Mass never be different in different places of the earth. Not only on the earth. If it is taken to the moon also, then its mass remains same, because quantity of matter contained in this paper is same on the surface of the moon also, on the surface of the earth also, in the space also. Everywhere mass remains same. But its value varies from place to place of the earth. If this paper is taken to North Pole, the force of attraction of the earth acting on this paper will be a little more, because value of G is a little more at pole. If the same is taken to equator or sea level, then G is less at that place in comparison with the pole. So the weight of this body, this piece of paper, will be a little less at sea level and at equatorial region. That's why weight varies from place to place of the earth, but mass remains same throughout the earth, and it remains same in the universe also. At any place the mass remains same. Next, its SI unit is kilogram. So very simple, you know this. Its SI unit is Newton. Since weight is a force, that's why its unit is Newton. There are certain important facts which we must know, and this very important fact which we have to understand. That's why I want to present this fact. Weight is more at pole than the equator. Why? This is fact, this statement is correct, but we have to understand, we have to discuss, and we have to prove that yes, it is correct statement. How can we say so? Weight is more at pole than the equator. The reason is weight of a body is the product of its mass and acceleration due to gravity, small g. We can write W equal to mg, and we know that mass of the body is constant, but g is inversely proportional to the square of the radius of the earth. Earth is flattened like this, and the value of g is inversely proportional to the square of the radius of the earth, means somewhere radius is less. If radius is less at this place, g will be more at this place, and somewhere radius is more. If radius is more at this place, then g will be less at this place. That's why g is inversely proportional to the square of the radius of the earth. Now g is more at pole because radius is less, and g is less at equator. Earth's radius is less at pole than equator, so g is more at pole, and the product of mass and g, that is what? The weight is more at pole than the equator. We can argue like this, and this statement is very important. That's why I'm talking about this. Now let's talk about another statement which is also very important. We have to remember and we have to be clear about this statement also. Weight is more at the bottom than the top of the mountain. This is a very important fact. Weight of a body is more at the bottom of the mountain than that of the top. Look at this is earth. At certain place of the earth, let's say we have mountain like this. Now we know that weight of the body is the product of its mass and small g. We can write W equal to mg, and we know that mass of the body is constant whether we go to bottom of the mountain or top of the mountain. Mass of the body is constant, but g is inversely proportional to the square of the radius of the earth. That's why g is inversely proportional to the square of the radius of the earth. That's why radius of the earth is less at the bottom of the mountain, so g is more at the bottom, and radius is more at the top of the mountain. That's why g is less at the top. G is more at bottom, less at the top. And so we can say that Earth's radius is more at the top of the mountain than the bottom. G is less at the top, and the product of g and mass, that is the weight of the body, will also be less at the top of the mountain. Is this clear? This is somewhat mathematical type of answer, isn't it? First we have to say W equal to mg, and m remains constant, and g is inversely proportional to square of the radius of the earth, and radius is this place, radius is less, that's why g is more. This place radius is more, that's why g is less. This way we have to conclude that W equal to mg. If g is more, weight will be more. If g is less, weight will be less. The same thing is repeating and repeating, isn't it? Yes. Now let's talk about other important facts also. Look at this. Weight of the body varies from place to place of the earth. Do you know that? Why? Weight of the body varies from place to place of the earth. Weight of the body is the product of its mass and acceleration due to gravity. W equal to mg. M remains same at any place of the earth. G is inversely proportional to the square of the radius of the earth. G is different in different places of the earth because earth is flattened at pole, bulged at equator. Same thing we are repeating, isn't it? And flattened at pole, bulged at equator, radius is different in different paths. That's why G is also different. That's why the weight, which is the product of m and g, is also different in different places of the earth. Okay, there is another fact also. We have to understand this also clearly. Weight of a body is more at sea level than any other place. Why? Weight W equal to mg, isn't it? We know this. W equal to mg. Yes, m remains same at any place, but g varies from place to place. Sea level, at sea level, radius of the earth is very less. Radius of the earth is very less. That's why g will be more. And that's why the product of more g and the mass, that is the weight of the body, will also be what? More at sea level. This way we can answer this question, or we can understand the fact behind this statement. Okay, now let's talk about free fall. What is free fall? Do you know what is free fall? We can say it like this: a body is said to be in free fall if it is falling with acceleration due to gravity without any resistance. What it means? Without any resistance means the body must be falling in vacuum, then only we can say there is no resistance. And free fall, it is possible only in vacuum. This is the definition of free fall. We can define free fall like this. But what is weightlessness? To understand clearly what is weightlessness, I want to give one example. Look at this is a spring balance, and let's say we are going to take the weight of a body. Here the body is suspended. Spring balance is used to measure the weight of the body. Beam balance is used to measure the mass of the body. Here we are measuring weight. That's why spring balance is used. Now this weight of this body is what? Weight of this body is the force of attraction of the earth acting on this body. With what force earth attracts this body towards its center is the weight of this body. And we can say that gravity force acting on this body is the weight of this body. And what we are doing here with a spring balance, we are suspending this object. It means the resistance force is applied by this spring balance. We are using a spring balance to hold the force of gravity. I mean to say, we are using a spring balance to hold the body, means against the gravity we are applying force by the use of a spring balance. And this force is acting in the upward direction. And this force is called reaction force. We are holding this body by using spring balance, and spring balance applies reaction force to hold this body. What is the pulling force of the earth acting on this body? That is actually neutralized by the reaction force used by this spring balance. That's why weight of the body can be measured by using a spring balance with the help of reaction force which produces in the spring balance. Yes, reaction force is used to measure the weight of the body. Is this clear? Now after this, now I want to talk about the weightlessness. Weight can be measured by spring balance in terms of what? Reaction force. But if a body is in free fall, then nothing is used as reaction force to hold it. During free fall, there is no reaction force at all. That's why the weight of the body is not measured. Weight of the body cannot be measured. Weight becomes zero. So we can say that a body becomes weightless during free fall due to the lack of reaction force. Such a condition is called weightlessness. If a body is at free fall, then no reaction force, no weight, and the body is said to be weightless. And this condition is called weightlessness. Okay. Now, let's talk about certain numerical problem which is related to free fall. Do you remember the equation of motion? Without the equation of motion, we cannot solve the numerical problem related to free fall. You are taught in class 9, there are many equations of motion. First, v equal to u plus at. Second, s equal to u plus v by 2 into t. Third, v square equal to u square plus 2as. And fourth one, s equal to ut plus half at square. All these were taught in class 9. We derived this equation in class 9. That's why I don't want to recall all the derivation. Just I mentioned these equations. Now look at this. First can be written this way also. Instead of acceleration a, we can write acceleration due to gravity g. In second case, since we are talking about the falling body, that's why height is considered, not the distance. In place of s, we can write s. All other part is same. And third equation can be written like this also. Instead of a, I'm writing g, and instead of s, distance, I'm writing h, because the body is dropped from certain height. Now, not the distance, we can talk about the height also. S equal to ut plus half at square can be written like this also. In place of s, in place of a, g. This way, the same equation can be written this way also. But it's not necessary to write particularly in this way or that way. But if somewhere v equal to u plus at comes like this, v equal to u plus gt, don't be confused, g is also a. Okay, now let's go through some numerical problem. Now by using this equation, how can we solve the numerical problem? I want to go through that. But before solving the numerical problem, you have to remember that if a body is dropped from certain height, then at first the body is at rest. That's why u is equal to 0. And when it falls down, its velocity goes on increasing and acceleration due to gravity produces. That's why a is equal to g, which is equal to 9.8 meter per second square. And when a body is thrown just opposite, when a body is thrown vertically upward, then its velocity goes on decreasing and decreasing and decreasing. At last, velocity becomes 0 at height, at maximum height. That's why final velocity is 0. And while going up, it comes under the gravity of the earth, and because of this reason, its acceleration becomes minus g. Why minus? Because it is moving opposite to the direction of the acceleration due to gravity. Instead of moving to the center of the earth, it is moving away from the center of the earth. That's why g becomes negative minus 9.8 meter per second square. We have to remember these points, and then only we will be able to solve the numerical problem. Let's have a numerical problem. When a body is thrown vertically upward with a velocity 15 meter per second, how high it goes up, how long it takes to go to that height, how long it takes to return back, what distance will it cover when return back. Look at this question. There are 4 questions, but only one information is given. The given information is initial velocity, it is 15 meter per second. But here we have some hidden information. What I told you just before this, if a body is thrown vertically upward, then acceleration will be minus g, minus 9.8 meter per second, and final velocity will be 0. V will be 0, a will be minus 9.8. 2 hidden informations are written here now. Now the question is height. How high it goes up. Height, it is denoted by h instead of distance s. Now how to calculate? UAVS. We have to source this symbol in the equation. Among these equations, UAVS, U here, A is present, UAVS is missing. U, A is missing. Here U, A, V, UAVS, all are present here. That's why using this equation we can solve this numerical problem. We have b square equal to u square plus 2as. If we take the value, then v square means 0 square, u square 15 square, and 2 remains same. A equal to minus 9.8, isn't it, into s. If we multiply and divide using calculator, you can get height. It is equal to 11.47958. After the decimal point we are taking just 2 digit, third digit is more than 5, that's why we can add 1 to second digit and the result is 11.48 meter. Now second question is how long it takes to go to that height. Now that can be calculated by using any equation out of those 4, because we have 4 information and including this height we have all information. That's why we have a equal to v minus u by t, t equal to v minus u by a. Taking the value of all these, u we have, a we have. If we use calculator, then 1.5306. After decimal point we are taking only 2 digits, that's why it takes 1.53 seconds to go to maximum height. Now third question is how long it takes to return back. Time taken to return back means how long it takes to go to maximum height, same time it will take to come down also, because acceleration is same. So we can say that time taken to return back is 2 into t. 2 into t equal to what? 3.06 second. Now last question, what distance will it cover when return back? Total distance. How high it goes up, the same distance it will cover to come back to the initial position. That's why this is equal to 2 into height, and 2 into height is what? 22.96. This way we can solve this numerical problem. Okay, we did a lot of matter related to mass and acceleration due to gravity and this weight also and gravitational constant. In another class I'll come with another matter. Now I want to stop this class. Thank you.